Hi, good morning, students. Last class we discussed about the Ampere's circuital theorem and how it is used to determine the magnetic field about a straight current carrying conductor. Okay, and we studied the variation of its magnetic field with the distance from its axial point. We discussed. Today we are discussing a different topic. It is force on an electric charge when it is moving in a uniform magnetic field or in a combined field of electric field and a magnetic field. Let us discuss. See, here a charge Q is kept in a electric field only. Electric field only. So the charge will be experiencing an electrostatic force. What is that electrostatic force? We discussed in the first chapter. A charge Q, when held in an electric field only, the electrostatic force is F equal to QE. F equal to QE. Where in vector form, F vector equal to Q into E vector. Right? So this is the electrostatic force experienced by the electric charge. It is experiencing the force and it will be moving. If it is a test charge with positive nature, what will be that? It is moving in the direction of that electric field. If it is a positive test charge, it will be moving in the direction of the electric field applied. Now, in the same space, we are setting a magnetic field of intensity B, a magnetic field of intensity B, uniform magnetic field, such that this charge is moving with a velocity V, and the angle between the direction of motion or velocity and the direction of magnetic field is theta. Then in a magnetic field B, where the angle between velocity and direction of magnetic field is theta, then the magnetic force experience is given by F equal to QVB sin theta. That is, an electric charge Q is moving with a velocity B in a uniform magnetic field such that the angle between the directions of velocity and magnetic field is theta. Then the magnetic force is expressed as F equal to QVB sin theta. Then we can write F vector equal to Q into, once we have discussed the cross product, A cross B is AB sin theta. So VB sin theta can be written as vector velocity V cross the magnetic field vector B. So we can express magnetic force equal to F equal to Q into V cross B. See, so if that electric charge is moving in this combined field, the net force will be the sum total of magnetic force and the electrostatic force. So the total force, the combined force from the electric field and magnetic field is F equal to Q into V cross B, the magnetic force, plus the electrostatic force, or we can write F equal to, Q is common, so Q into V cross B plus E vector. So in a combined electric and magnetic field, the total force is Q into V cross B plus E, which is the sum total of the magnetic force and the electrostatic force. Now see this, in a magnetic field only, what is the magnetic force? F equal to Q into V cross B, which is QVB sin theta. The magnitude of forces F equal to QVB sin theta. Suppose the velocity vector and the direction of magnetic field is at right angle, that is theta equal to 90 degree. That is, when theta equal to 90 degree, that is velocity vector perpendicular to the direction of magnetic field, the force is maximum, which is QVB only. So the maximum force is experienced, maximum magnetic force is experienced by the charge when its direction of velocity is perpendicular to the magnetic field direction in the space. Now, in such a situation, to find the force experienced by the charge, electric charge from a magnetic field, when its velocity vector perpendicular to the direction of magnetic field, we are applying Fleming's left hand rule. So Fleming's left hand rule is used to determine the magnetic force experienced by the electric charge when it is moving with a velocity perpendicular to the direction of magnetic field. And it states that if you stretch the thumb, forefinger and the central finger of the left hand mutually perpendicular to each other, we are stretching thumb, forefinger and the central finger of the left hand mutually perpendicular to each other, such that this central finger point in the direction of velocity or motion and forefinger in the direction of magnetic field, then the thumb will be pointing in the direction of force experienced by the charge from that magnetic field. So what we are using? We are using Fleming's left hand rule for what? To determine the direction of magnetic force experienced by the electric charge when it is moving with a velocity perpendicular to the direction of magnetic field in the space. Okay, and F equal to QVB. Now let in space there is a magnetic field pointing into the plane of the board as it is shown by the into the plane of the board. Here the magnetic field is pointing into the plane of the board, and let charges moving along the plane of the board with an angle perpendicular to the direction of magnetic field. So magnetic field is into the plane of the board and this charge is moving along the board. So now the angle between the velocity and the magnetic field is 90 degree. So force is F equal to QVB. So what is the direction of that force? Using left hand rule, magnetic field into the plane of the board, velocity, so force is along this direction. Now this particle is moving and let it is reaching here. It is moving and it is reaching here. Now again its velocity is like this, perpendicular direction of magnetic field. So what is the direction of force? Magnetic field into the velocity along this direction. So the force is like this. Here also the charge comes here. Here the velocity is like this. And again by applying left hand rule you can see that the magnetic field is into velocity like this and the force is pointing like this. Let the charge reaches here. So the velocity along this direction and magnetic field into the plane of the board and the force is like this. So in this case we can see that when the particle is moving with a velocity direction perpendicular to the direction of magnetic field, it is following a circular path or its motion is circular. So when the charge is moving with a velocity perpendicular to the direction of magnetic field, uniform magnetic field only, then it will be executing a circular motion. Now for the circular motion of a mass of m, the radius of the circular track is r, then we have the centripetal force equal to mv square by r. Here the charge is having a mass m, it is moving with a velocity v along a circular path of radius r, then the centripetal force is mv square by r. But actually here the centripetal force is the magnetic force experienced. You know, for the planets to revolve around the sun, they are experiencing gravitational force. So their centripetal force is the gravitational force between the earth or the planet and the sun. Here the centripetal force required for the particle to move, it is the magnetic force. We are writing F centripetal equal to the magnetic force, that is mv square by r equal to qvb, or we can write v equal to qbr by m. Here the velocity of the particle in a circular motion where the magnetic field is perpendicular direction of velocity, then the velocity v equal to qbr by m.